If each resource type has several resource instances, here we can use a deadlock detection algorithm. Here we have the N is the number of threads, M is the number of resource types. These are data structures we use in the deadlock detection algorithm. Available, allocation, and request. Available is a vector, m-dimensional vector. It indicates the number of resource instances. In the banker's algorithm, we have the same data structure. Allocation matrix. This is the N by M matrix. This allocation matrix defines the number of resource instances currently allocated to each thread. In the banker's algorithm, we also have the allocation matrix. And the third data structure is a request matrix. Request matrix is an N by M matrix. This request matrix indicates the current request of each thread. If the request ij equal to k, it means the thread ti requests k instances of rg. In the banker's algorithm, we don't have request matrix. We have need matrix. The need is very similar to the request matrix. This is the deadlock detection algorithm. First step, we initialize two vectors, work vector and finish vector. Work vector indicates the available resource instances, and the finish vector shows if a thread can finish or not. These two vectors are very similar to the two vectors we used in the banker's algorithm. The first step, we initialize work and finish these two vectors. Work is initialized as available vector. Finish indicate if this thread can finish or not. Initial value is false. All the threads are not finished. This is the initialization step. The step 2, we are trying to find thread ti such that the thread is unfinished, and also this thread request is less than or equal to current available resources. Work indicates the current available resource instances. If the request less than work, we move to the step 3. Step 3 means update work. Work equal to work allocation I. This means this unfinished thread can finish, and this thread will release all the resources allocated to it. So we update current available resource vector at the resources allocated to thread ti. And we also set this thread ti can finish equal to true. So we repeat step 2 and 3. Repeat this step 2 and 3, try to find all the possible thread that can finish. Now, when there's no thread that can finish, there's no unfinished thread, its request less than work. If this thread doesn't exist, we go to the step 4. So step 4 will check if for all thread finish is true or false. If there's some thread the finish is false, this means the system is in a deadlocked state. There is a deadlock or a deadlock exists. Moreover, if the finished I equal to false, this means the thread Ti is deadlocked. If for all the thread finished equal to true, means there's no deadlock. Okay, now let's take a look at an example. This is the data structure we need to use in the deadlock detection algorithm. Allocation matrix, request, and available. In this example, we have 5 threads. So n equal to 5 threads. And the three resource types. So m equal to 3. We have the resource A, B, C. These are resource type. The resource type A has 7 instances. Resource type B has 2 instances. Resource type C has 6 instances. Now the available is a 3-dimensional vector. It indicates the current available resources. Now the current available resources are 0, 0, 0. So now we don't have any resource instances available now. Allocation is a 5 by 3 matrix. This means that T0. Now the T0 holds 1 instance of B. So this 1 instance of B is allocated to T0. And T1 holds 2 instances of A. So the 2 instances of A are allocated to T1. So this is the allocation matrix. The request matrix. And for the T1 request to A and to C. This means that the T1 thread requests 2 instances of A and 2 instances of C. Now from this matrix, we can see T0 doesn't request any resource instances, and T2 doesn't request any resource instances. Okay, now let's use the deadlock detection algorithm to see if there is a deadlock or if deadlock exists. So first step, we initialize work and finish to vector. Work is equal to available 0, 0, 0. Finish, all the threads are not finished. Not finished, so false. So we start from the thread 0. Thread 0 request is less than or equal to work. So the T0 doesn't request any resources. T0 gets 1 instance of B. T0 start execution and then terminate or finish. T0 can release this 1 instance of B. So T0 can finish equal to true. And we update work. Work is equal to work plus allocation. T0's allocation. Now after T0 terminates, we get 1 instance of B. And then the T1's request to A and to C. Now current available resource instances, 1B. So for T1 request is greater than work. T1 cannot finish. and then T2. Okay, so we have the T0 goes first. And then T2 doesn't request any resource instances. T2 already gets all the needed resources. T2 can start execution and then terminates and then release these resource instances. So here the T2 request is less than work. So T2 can finish equal to true. And then we update work. 303 plus 010. So now we have 3 instances of A, 1B, and 3C are available. And next one is T3. T3 is unfinished. It's unfinished. Also, the T3's request is less than work. That means that T3 can get this required resources and start execution and then terminate. Okay, so we have T2 and T3 can finish. T3 finish. After T3 finish, T3 will release these resources. Now we update work vector. So add the 2 here, we get 5. Add 1 here, we get 2. Add 1, 2, 3, we have 4. And the next one is the T3. Next one is a T4. T4 is unfinished, and the T4's request 2C is less than work vector. So T4 can finish, and we update work. T4 release 2 instances of C, add it to work. 6 T4. And then we can see we still have one unfinished thread, T1. T1 is unfinished. T1's request is 2A and 2C. This request is less than work. This can finish, and then we update work. This 2 plus 5, 7. And 0 plus 2, 2. Yeah, I think I read the wrong number. This should be 4. 2 and 4. The T1 is the last thread. Okay, now after this deadlock detection algorithm, we can see that all these threads can finish if they execute use this order, and they can finish. So there's no deadlock. No deadlock. And now if I change this data structure, change the request. Now the T2 in this data structure, T2 doesn't request any resource instances. And now assuming T2 requests 1 instance of C. So we change the T2's request. From 000 to 001. Now let's see if there is a deadlock. Now first step, we initialize finish false, 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 false. And we initialize work vector. Now we start from T0. T0 is unfinished, finish equal to false. And and the T0 request is less than or equal to work. So T0 can finish and T0 release 1B. And then T1 is unfinished, but T1's request is greater than work, so T1 cannot finish. And then T2, thread T2 request 1C, and now we don't have any instance of C available, so T2 cannot finish. And then T3 request one instance of A, and now we don't have the instance of A, so T3 cannot finish. And then T4 request 2C. Now we don't have resource instance of C. So now after we checked every thread, now the only T0 can finish. T1, T2, T3, T4 cannot finish. Finish equal to false. That means the system is in a deadlock state. The thread T1, T2, T3, T4 are in deadlocked state. They are involved in deadlock. Okay, this is a deadlock detection algorithm. Now we have the deadlock detection algorithm. Now the next question is when and how often to invoke this deadlock detection algorithm. It depends on how often a deadlock is likely to occur and how many threads will be affected. If deadlocks occur frequently, then the deadlock detection algorithm should be invoked frequently. So normally the deadlocks occur only when some thread makes a request and cannot be granted immediately. So this request may be the final request that completes a chain of waiting thread. So in this case, we can invoke deadlock detection algorithm every time a request cannot be granted. Okay. In this case, we can identify the deadlocked thread or the threads that are involved in the deadlock. But the problem is invoking the deadlock detection algorithm for every resource request will generate the considerable overhead in the computation time. So we need the less expensive approach. The less expensive approach is to simply invoke the deadlock detection algorithm at defined intervals. For example, we invoke the deadlock detection algorithm once per hour, or when the CPU utilization is below 40%. Okay. This is the deadlock detection algorithm. This video will conclude here, and we will talk about the recover from deadlock in the separate video.